So looking at this gravitational focusing, or the fact that we've now increased the cross-section, I'm going to write down what this larger cross-section is, which is the dashed circular line, and it's left for the problem class to actually get this cross-section, which you can derive using conservation of energy and conservation of angular momentum. It's quite a nice problem that James shows in the problem class video. And it is related to this geometrical cross-section multiplied by a term here, which is 1 plus the escape velocity squared divided by the random velocity squared. Now, what is the escape velocity? This is, you might remember, is the speed that an object needs to get away from the gravitational pull of the object. So we could consider this central star shown in the yellow circle, and it's the speed to escape its gravitational pull or to become unbound. So this, you can see why this would define this dashed circle where it's the sort of maximum circular area over which these stars are attracted to each other. Now, if you plug in that the escape speed for a star, an average star, which is similar to our sun, is about 620 kilometers per second, then if you plug that in with the random velocity that we saw before, you get that the ratio of the cross-sections is the gravitational cross-section is about 1,000 times larger than the geometrical one. But we saw that the time between collisions with the geometrical cross-section was so large that even this factor of 1,000 still means that it's extremely rare for stars to ever collide within a galaxy. Okay, so moving on, we're now going to go back to the first calculation we did, which was the period or the time it takes for the sun to orbit all the way around the galaxy. But now we are going to look at a large collection of stars and gas at different radial distances from the center of the galaxy and look at what that orbital velocity is. And the interesting thing is that we see from observations a different relationship, very different than when we'd expect based on the visible stars. So shown in this diagram at the bottom is what's known as a rotation curve of a spiral galaxy, where you have on the y-axis the orbital speed and on the x-axis the radius from the center of the galaxy. And what's quite nice here is that we have an image of the galaxy that's being studied, which is M33, the Triangulum galaxy. And that gives us a scale that once you get to about 5 kiloparsecs away from the center, you're away from most of the stars and most of the visible mass. And in that sense, we could consider when your distance is beyond that, you can roughly consider the mass inside to be a sphere, which then shrinks down to a point. You can actually use Newton's law for relating the centripetal acceleration to, and then you multiply by mass, and that's then equal to the gravitational force. So if we write that out, you might remember that we get v is the orbital speed squared divided by the radius is equal to the gravitational constant g times the mass that's contained within divided by r squared. So we can then solve for v, and that's pretty straightforward, that v is equal to g over m, the square root of that, and then that's multiplied by r to the minus 1/2. Okay, and this dashed line in the graph, if you're looking between distances of greater than 5 in radius, in 5 kiloparsecs, I should say, that falling curve is r to the minus 1/2. That's the shape that you'd expect for the velocity. However, what is observed is a much larger velocity, and it's not dropping off. In fact, it's slightly rising. And this is interesting, which we will get to probably next week, when we look for evidence that there is more mass than we can see. And this is what's known as dark matter, that extends much further beyond the visible stars and gas in the more central part of the galaxy. So we're already learning something interesting there. All right. So continuing on with the theme of these spiral arms, we can try to ask, why are they this shape? Why do we see a spiral structure? And now that we've seen from our rotation curve that the velocity, the orbital velocity, is relatively flat or doesn't change much when you get to the outer parts of the spiral arms, you have roughly a constant orbital velocity, then that would cause differential rotation. And we can see why if we write out just the definition of the angular speed, which is omega would then be a function of r, where r is this radius away from the center of the galaxy, is equal to v over r. So if we're saying that v is constant, then as you get further out, larger radial values, you have a smaller angular speed. So what you can then do is a little simulation that's shown in the bottom left and middle graph, where you start with two straight distributions of stars, basically a straight red and a straight green line that go across the x-axis. And then as time progresses, the outer part is rotating slower than the inner part, so it is going to trail. And you start to wind up or create a spiral pattern. Now, what's shown on the bottom left is after 200 million years, and then after 1 billion years, you have a very tightly wound galaxy. Now, this is a problem, and it's known as the winding problem, because if you go back and look at the shape of spiral galaxies, so I'll flip back and we could look at This is the projection of our own Milky Way, or here is the Pinwheel Galaxy. We only see these arms around maybe once around, not many, many times wound around. And so this even looks more extreme if you go to an age of our galaxy. I've gone too far. There we are. Sorry. Back again. Of about 10 billion years. So that cannot be the explanation for why we see these spiral patterns. Instead, what we think about is that this spiral structure is more stationary and that the stars actually orbit through these spiral looking structures. So again, it was more like 200 million years, which is a relatively short time compared to 10 billion years for the sun to orbit around. And during that time, this we would think that this spiral structure is roughly staying where it is. And the way that's possible is shown on the bottom right diagram, where you could think about elliptical or slightly elliptical orbits. They're not too elliptical, but a little bit, that are actually tilted in a way such that you start to actually see, if you look at where the lines are closest together, a higher density of these orbits that trace out roughly the shape of spiral arms. And they would stay that way, assuming that you have a roughly even distribution of stars that are in these orbital paths. So in other words, tracing out these slightly elliptical curves. And just the higher density of stars, where you have these lines closer together, make it look as though these are arms of